Hello, welcome to lecture 23, which is a continuation of lecture 22. So, here we will solve another example to further get clarity on the theory that we have discussed. So, let me write down the example. So, we have a beam with a symmetric I cross section as has been shown in the figure. So, each portion, the two flanges and the web of this I section has a length of 2h. Now, a shear force F is applied in the y direction. So, a shear force F is applied in the y direction. So, let me just name this as 1, 2, 3, 4, 5 and 6. So, the force F is applied at point 5 through the centroid, and it is given as the magnitude of the force is F. So, we need to find the shear flow distribution in the I section due to the applied force. So, that is the problem statement. So, if I try to summarize what the problem has said, so we know therefore Sy is equal to F and there is no shear force applied in x direction. So, Sx is going to be 0. Now, since the the cross section of the beam is symmetric about x axis, I x y is going to be equal to 0. Now, if I substitute these conditions in equation 1 that we have, that is, or equation 3 that we have, we say that Qs minus Q0, which is given as minus So, this is the expression that we have been using. Now, let us see what happens in the expression. So, S x is equal to 0 as well as I x y is equal to 0. So, this is equal to 0. So, this expression simplify to a considerable extent and we are just left with minus S y by I y y by now out of this 2 cancels out. So, we are left with minus S y by x x into 0 to s t y d s. This can be further written as minus f t by I x x into 0 to s. So, that is the expression we have for this particular cross section. So, let me call this as equation 1. Therefore, we see that we do not need to find out both the sectional property I x x and I y y. We need to find only I x x and that is what is required. So, let us find out I x x for the given cross section. So, for the given cross section the contribution from the web will be 1 by 2 h cube into t. Now, the contribution from the two flanges are going to be 2 into 2 h t, the area, into h square. So, if we sum this up, this is going to be 14 h cube t by 3. So, that is the I x x. So, therefore, let us the next step is to find out q s and find out the distribution of the shear flow in the cross section. So, let us start with flange 1 2. So, for flange 1 2 we are moving in this direction. Here I have s equals to 0 and here s is equal to h by 2. So, my s is between, sorry, it is not h by 2, it is going to be h. So, s is between h and 0. I do not need to express x in terms of s because it does not appear in equation 1. Instead, I have to just express y in terms of s and y in this case is just minus h. So, if we plug this in the equation, we see that if we plug this in into the equation, we will see that q12 s, now q0 is q1 which is of course equals to 0 and that is going to be minus f t by I x x into y is minus h into d s. So, that is going to give me f t h by I x x into s. So, this is the expression for q12. Therefore, we can say that q12 s is going to be f t h So, let me call this as equation 2. Now, from this expression I can find out the value of Q 2 as Q12 into S is H, and that is going to be F T H square by I x x. So, this is the expression for Q 2. So, let us now that we have found out the expression for Q 2, let us see how is it going to be distributed. So, let me draw the section once more. So, let me carry it forward. So, Q1 to S we have found out to be F T H S by I x x. So, this was my equation 2, and from equation 2 we have found out we have got Q 2 to be equal to F T H square by I x x. So, let me try to draw the distribution therefore. So, if I draw the distribution at Q 1 it is equal to 0, and the distribution is going to be linear. So, this is how it is going to be distributed. So, this value is F T H square by I x x, and this line is given as F T H S by I x x, and the shear flow is in the positive direction that we have considered for S, and this is Q1 to S. This is the direction, and this is the values, and this is the direction. Okay. So, this is how we can find out the shear flow in the flange 1 2. Now, let us move into web 2 3. Now, for web 2 3 we are going to have S between 2h and 0. So, we have S equals to 0 to 2h, and we need to find out only y. So, y is going to vary as minus h plus s. When s is equal to 0, y is minus h, and when s is equal to 2h, y is h. Therefore, from the previous expression we can say Q23s minus Q2 is going to be minus Ft which in turn can be written as minus Ft by I x x minus h plus s into ds. Say if you evaluate that, then we have Q23s, and Q2 is minus Ft h square by I xx, and that is so. Let me so this is the other expression for finding out the shear flow distribution in web 2-3. So, let me call it as equation 3. Now, from this equation 3, we can find out the shear stress distribution in web 2-3. Now, we can always find out Q3, which is going to be Q23 of 2H, and that is going to be Ft H square by I xx minus Ft Now, we can see that this and this is cancelling out, and Q3 remains to be Ft H square by I xx, which is equal to Q2. So, this is also true from other perspective, that because there is a symmetry in the cross section, Q2 has to be equal to Q3, because Q2 and Q3 are symmetrically placed about the x axis, and therefore, this is the expression that we have. Now, if we try to draw the shear flow distribution Q23S, this is going to be looking like this. So, this will no longer be linear, but it is going to be quadratic distribution, and it is going to look something like this, and this is the direction of Q23S. So, this is Q23S, and this is given by equation 3. This is how we can find out the distribution of shear flow. This is symmetric, though I have not drawn symmetry, it is symmetric about the x axis. So, this is how we can draw the obtain the shear flow distribution in web 2-3. So, following the same procedure, we can find out the shear flow distribution in the flange. I have to remove this thing. So, I have to call this as 3, this as 5 maybe. Sorry, I did not represent what I said in the. So, in the previous expression also. So, this is going to be 5 and this is. So, this is 3 and this is 5. So, we can use the same methodology that we have adopted for flange 1, 2 and web 2, 3 to find out the distribution of shear flow in all the portions of the cross section. But on the other hand, we may not go through this long calculation and just use the symmetric property of the cross section and evaluate the shear flow distribution. So, if we use the shear symmetric condition, then the shear flow here would be just symmetric to that of the. So, if we just use the symmetric condition, this is going to be symmetric, this also has to be symmetric. The shear flow is going to be like this. The shear flow has to be so a good exercise would be to evaluate yourself what would be the shear flow in the remaining portion of the cross section and to see whether they follow the symmetricness that I have drawn. So, with this we will complete the examples that we have we plan to do for finding out the shear flow distribution due to applied shear forces in a thin walled open cross section. Next, we are going to move into a new concept which is called the shear center. Now, we are going to talk about a new concept which is called shear center of a cross section, of a beam cross section. Now, what is shear center? Before we go into the definition of shear center, let us try to understand about shear flow due to shear forces and due to torsion. Now, shear flow in a cross section can happen because of two reasons. So, shear flow in a beam cross section can happen due to two reasons. One is torsion, torsional moment, and the next is shear forces. Right. So, both of these are going to produce a shear flow in the cross section. Now, if we apply a shear force Sx and Sy, the shear force is also going to produce a torsional moment about the cross section. So, if we apply a shear force somewhere on the cross sectional plane, so if we apply a shear force Sx and Sy, then this shear forces will also produce a torsional moment about a given point on the cross section. So, if we choose any point on the cross section, if we choose any arbitrary point P on the cross section, both Sx and Sy is going to produce a torsional moment about the point P. Now, this torsional moment in turn is going to produce a shear flow. Therefore, the cross section will experience two shear flow. So, it will experience shear flow 1 and it will experience a shear flow 2. So, this shear flow would be due to Sx and Sy, and this shear flow will be due to torsional moment produced by Sx and Sy. So, once you understand this concept, then we can define shear center as the point on the cross section of the beam such that when the shear forces are applied through that point, there is going to be no resultant torsional moment in the cross section of the beam. So, let me write down. So, shear center is the point on the plane of the cross section through which the shear load should act to produce no torsional moment in the cross section of Okay. So, this is the definition of shear center. Let me just explain it. So, shear center is a point. So, I have drawn this point. So, shear center is a point on the plane of cross section of the beam such that the shear forces, if the shear forces passes through this point, the shear center, then there would be no resultant torsional moment in the cross section of the beam. So, how is that possible? Because our intuition says that if Sx and Sy passes through the shear center, it will produce some torsional moment, but this torsional moment will be balanced out by the shear flow distribution in the cross section of the beam. and thereby the net resultant torsional moment in the cross section is going to be 0. So, what we can rewrite this definition as if Sx and Sy, so let me use the acronym SC, passes through SC, then Q2S is going to be 0. What is Q2S? Q2S is the shear flow due to torsional moment produced by Sx and Sy. Okay. So, therefore, the net, if the Sx and Sy passes through the shear center, the net torsional moment on the beam is 0. So, and therefore, we need not consider Q2S. So, we will talk more about the shear center in the next lecture. Thank you.